Look at that. Alles werkt. Nee.
Maar ik denk niet dat het überhaupt komt met dat hij ons helemaal Nou ja, wij hadden gezegd dat we niet gaan inviteren, want we dachten dat we net erbij af. We kunnen in de avond niet die middelvinger en dat soort dingen optreden. Hij zei dat hij wel had gezegd.
Hello. Good morning. Welcome to the fifth lecture for the computer networks. I promised some students that I will talk today about the Wireshark assignment, but I haven't finished all the grading, so the ordering for the Wireshark assignment, so I cannot discuss it this week. We will discuss it next week, and then also at the end I will also have kind of a wrap up for. So next week will be maybe we will handle the last slides, and the week afterwards we will kind of have a whole overview of all the theory, all the practical assignments, and how everything is related with everything else. So hopefully that last lecture will help you get a view of the big picture and how everything fits with everything else. Layers and also details inside the layers, ETLs, stuff like that. So that's a little bit about the planning. I see that we also have something like 30 students present out of an expected 150 students and 40 students. So does anyone know what's happening or why there are so few students?
They gave up.
They give up. Okay, good. Well, hopefully this is not true, and hopefully the students are watching the lectures at home and learning from that. Yeah, we'll see what happens at the end of the course. The results of the practical and the results of the theory test. Well, thank you all for coming. Today I'm going to try to explain some things. I will write we'll solve some exercises together, so it will be a little bit of an interactive, cooperative session. So I brought my tablet with a pen, and we will kind of sit and solve some of the assignments together. The YouTube thing I'm testing for a lecture I'm giving in the next period. So this is just it's not for you guys. It's just to see how everything works. It lasts for the whole lecture. Yeah. So just an explanation. Today we are going to talk about the internet, the IP layer. So don't mix up IP as an IP address and IP as an IP layer. The first part of the lecture we will talk about the internet protocol in general, and then we will talk about IPv4 specifically, and about subnets and subnetnets. This is something that you have already encountered a few times, and it's something that you will encounter throughout this course. Some terms are very similar to other terms, but mean completely different things. And in order to understand how computer networks work, you have to also understand the differences between these terms. And because this will be important when you are later on reading manuals or writing your own manuals, you will also need to be very specific and very accurate with your terminology. And this is unfortunately something that you're going to be evaluated on during the theory test. I also try to stress it a little bit when I evaluate you during the practicum sessions, but if I tolerate it in the practicum a little bit, in the theory test, it's multiple choice, and if you misunderstand or have a little bit of doubt about some of the term and which one does it mean, then you will choose the wrong answer and then you will not be able to pass. So it's very important. I will stress some of them today, and in the last lecture when I have the overall, I will also show some of the similar terms and show you guys what each of them mean, and so that you can also remember it. Yeah, so these are the topics we are going to go through today. Let's continue. So the network layer is layer 3. Layer 3 of the 5 layer system, the Department of Defense layer system. We have I have the layers over here. I cannot change the slides because these slides are used in all 3 locations. But what I did as a solution is that I have, let's see, I have another set of slides that I have here, so we can jump between these presentations from time to time. But the idea is that the other slides are the same for all the locations. That's why I have 2 presentations running at the same time. So layer 3 is a network layer. It's that one in the middle, also called the IP layer. So IP layer, IP address, these are very similar names. It's almost the same name, just one extra word. But when we are talking about the IP layer, what we mean is that is the layer 3 in our network model here. And then later on, we will talk about IP addresses, IPv4, IPv6. So now, when we talk about layer 3, layer 3, which we are going to talk about here, is the network layer. And inside network layer, we have known protocols, which are IPv4 and IPv6. They will also see clearly why IPv4 is inadequate and why we need a follow-up for it. And then what does the network layer do? This is something that we are going to deal with also in the third assignment. In the third assignment, we were going to set up routers in the packet tracer program. And there you will see that, as we discussed before, routers connect a network between different computers. And then these networks, based on IP addresses, can send a message from one computer to another computer. And this is, of course, a very simplified model of how the internet would look like. But you can see that if I'm sending a message from this end system to this end system, that there are different routes that can be taken. And then this route will also lead to this end system. It can go directly through here, it can go through here. And you can see that if it goes to this router, then it will not be able to go to that end system. So this router is the wrong path. But choosing which path those packets go through in order to reach one end system to the other end system, that's all what we are going to deal with when we are talking about the IP layer. So here we see that this it's not confirmed that when you send a packet that is going to reach its destination. So you see that when we sent a packet, you saw that we have the TTL, the time to live, and then the time to live, it just counts the number of hops between different routers, and then it will see whether it will reach the end destination or not. So before you send, there is no confirmation, 100% confirmation that there is a link established to the end system and that you are going to reach the end system that you are trying to go. So it's a similar concept to the UDP packets as we saw in the Wireshark assignment. You see that when you send the UDP packet, it's a send and pray model, but this time not in layer 4. UDP and TCP were decided in layer 4. Here we are deciding also in layer 3 that we are sending these packets. Also, TCP packets in layer 4 are sent through the IP layer, and then some of the TCP packets are not don't reach the destination. But what we have with the TCP packet is the acknowledgement. So when you send the TCP packet to the source and you don't get the acknowledgement, you know that the IP layer has come down. The packet hasn't reached its destination, so layer 4 is smart enough to send this packet again. So we have again some overlap. We have send and pray for the IP layers on layer 3, and we have also in layer 4 UDP, which is a protocol that uses the send and pray method, but we have the TCP in layer 4 that uses confirmed transmission of data. For layer 3, there is no error check. And yeah, so you don't know from beforehand, so from what is it called? For off, whether you are going to reach your destination or not. Okay, so here we are talking about the TTL. The TTL is decided in the, yeah? Where? Oh. What are you talking about? Over? So if you want to establish a connection between the server and wait for confirmation, like we talked about TCP. With TCP, there's the first handshake protocol, and then you have a lot of waiting time. So you have this overhead that you need to wait for until the connection is established. If you have to do that in TCP, and then you also have to do that, so TCP is layer 4, and if you have to do that also for layer 3, then there will be so much overhead, so much traffic time just to confirm things, then you will lose lots of time. So it's better to just use the handshake in the layer 4, and then for layer 3, just send and pray and see if something doesn't reach the destination, then you resend the packet again. Here we are talking about the TTL. As you remember, there are two types of TTL. The TTL we are talking here is the TTL for the layer 3 headers. So if we look again at the layer 3 headers over here, you will see that part of the header is the time to live. The time to live is a number, and as we remember, we saw in the slides, for Windows machines is 128 hops, for Unix machines is 64, etc. These are the number of level 3 routers that the packet can go through from one router to the other router until if it's lost, it keeps jumping between routers, it doesn't reach the destination, then it will kill itself. This is the example we kept saying, and you can see here. So this is our encapsulated packet, right? So
the packet is generated at the application layer, and then it's put inside another TCP or UDP packet, and then it's put inside the IP packet, so the layer 3 packet, and then inside the layer 2 packet, etc., etc. The layer 3 packet is the one that has the time to live. So this time to live is inside this header here. And then we also know that when we are sending the packet through the network, then every time it goes, when it goes through a switch, it will not be opened until layer 3. So only the packets will be opened until layer 2. It will check the next MAC address that needs to be sent to, and then it will send it to on its way. But then when it reaches a router, then the router will open the encapsulations until layer 3 to see which IP address is the destination. So it will open all the encapsulations. It will open this Matroska doll thing until it reaches layer 3. It will read this header. It will read this header, see the source address and destination address. The address that's meant here is the IP address. And then what it will do is that it will change the time to live to a -1. So it will read 128. Okay, I'm already reading this, so I will reduce this by 1 and send this packet. And it will continue to be reduced until it reaches 0 or until it reaches the destination that it's aiming for. Is that part clear? This is how the process works. If there are any questions, now is the time to ask.
Do we need to do any other types that's in the header, like corrective processing?
You learn it for toots. So the toots is described in that summary sheet. I don't know that what's for the toots.
But I'm
mostly talking about we understand how the theory works. Yeah. So time to live starts at 128 when the first computer that is sending the packet is making all the encapsulation. So from the, let's see, where is it? Oh, so from here. So from here we have the source computer that you send from an email, for example, and then it will do all this encapsulation. So it will put one inside the other. It will do this encapsulation thing. And then the first time it does the encapsulation, it will start, if it's a Windows machine, it will write 128 as a number, as a time to live. So every time that computer sends a packet, it will always start with 128. And then it will send it through the network, and the network will look something like this. So the network will look something like this, and then of course the internet has much more routers. So that when your packet is trying to reach from here to America, it will go through like 10, 20 routers if it's going in the right direction, if it knows where it's going. But sometimes the packets get lost. So every time it goes, the packet goes through a router, if everything goes well, your packet will go from here, 128, to here. It will read until layer 3. It will reduce it to 127, send it to here, 127 to 126, 126 to 125, and then it will reach the destination. So then it's still okay. But imagine that it gets lost for some reason or another, like it went here and there is no way to go to the destination, and then it keeps bouncing between these two routers. In order not to fill the network with all these lost packets, it will keep counting down. So from 128 until 0, and then when it reaches 0, it will be like, okay, this is hopeless. I will just kill myself. The router will just not send it on, it will just stop it. And this will be there. So that's the idea of the TTL. Now, if you remember in the previous lecture, we talked about another TTL, which was for the domain name service. When you ask for a domain name, then the domain saves it in a cache, and then it will keep counting down some time. If no one else asks for the same domain name, it will remove it from the cache. and then it will be like something like 5 minutes. So, okay, someone asks for this website, I'll keep it for 5 minutes. If someone else asks for it, that time to live is also called TTL. So it's one of the other confusing things. It's also called TTL, but that one is counted in time. This TTL is in the IP header, and this one is counted in hops. Hops is how many routers you jump from one to the other. The other TTL is counted in time, is for the domain name service. It's something to keep in mind. It's very confusing, I know. Hope they should have used different names, but this is how it happens. Okay. Oh, so then here is a question. So when you're a router and you see that there is a TTL of 1, and you know the IP address of the destination, so I know that the IP address of the destination is in the header, and I know that I'm sending it to another router, which is not, I think it's on the way to that IP destination, but it is not the destination. So I know that it's going to die, because it will reach the next router and the TTL will become 0 and it will kill it. So the question here is why does the router indeed send that packet to the next router, even though it knows that it will never reach the destination? Does anyone have an idea? Yeah.
The router from the data.
It can know, because it knows the IP address of the next router it's sending it to, and in the header it also knows the destination IP address. Yeah, so it's counting the time to live down, and it knows that it will never reach this destination, because it knows that the IP address it's sending it to is different than the IP address of the destination. Yes?
Misschien dat de router geen andere oplossing weet, dus hij weet dat van wij gaan nadat hij niet sturen, dus hij stuurt mag worden. En dan weet hij niet dat. Anders kan hij niet weggooien.
Niet weggooien. Ja, bijna. Ja, toch een idee?
Hij blijft procedure om tegen het time to live af te stellen, dat de taal blijft dus ja, maar wanneer niet.
En ze zijn er niet voor gemaakt om te zien van, oh, als dit niet de source address is en hij heeft 1 TTL, dan killen we hem alvast maar, want het heeft geen zin. Je moet hem gewoon doorvullen, dat is geprogrammeerd. Yeah.
Yeah, you're getting closer and closer. So the idea is that the routers are not very smart, and so if you make them very smart, it will take they will be more expensive because the processor will need to do a lot of checks before it sends that packet, and it will also take time because it will be an extra check. So you have to have an if statement. If the TTL is 1 and the next IP address is not that IP address, it has to compare the IP addresses, then kill that packet. And what they found out is that this is again overhead. So overhead is like extra work that you need to do. And the profit they would gain, so the speed that you gain from not sending that packet to one extra router is less useful than just doing it very, very fast, send it immediately to the next router, and then the next router will kill it anyway. So it's all about weighing the benefits and the costs, and then choosing which way is actually more beneficial for the network. So, thought.
Router, like this, I check on the details, but this condition is very different than we thought it is.
If the TTL is 0 and the next router is the next IP address is the correct destination, then the packet will also be dropped. Which actually is a smart question, because then why not just send it one more time? But again, the router is not smart enough to see this because it's not designed to check for it. It will immediately see that the TTL is 0, it will kill the packet and wait for another packet to be sent. So IP and fault detection. Some walks in will not do this. I know it's nice, but sorry. We saw that there is no confirmation in the communication between you and the destination, so it's kind of a send and pray. So what kind of fault detection does the IP layer have? The things that we already looked into. So TTL, if the TTL is expired, then you are not able to reach your destination. We saw that the ping request, you guys have already tried it with the first assignment, and you are and you saw that you can send a ping request, or sometimes it's called a network request. Basically, you just send a packet to the destination. You say, "Are you there?" If yes, send me a reply, and then you can get a reply from the server that is saying that yes, I am here and I can hear you. So you can see that the network connection is working well. So these are some basic tools that are used to check whether the network is working or not until the IP3 layer. So if the communication doesn't work, but your ping works, then you know that the fault is somewhere above the layer 3. If the ping also doesn't work, then you know that the ping is like the most simple IP3 function that you can use, service that you can use. If that doesn't work, then you know that the problem is in the IP3 level. So some router between you and the destination is not sending the packets properly. Okay, so now we switched. So it looks very similar, but now we switched from the IP as in layer 3 to IPv4. IPv4 is one of the protocols that you can use in the IP layer. So IP layer uses 2 different protocols. One is IPv4, one is IPv6. IPv6, as far as I can remember, they were trying to get people to switch to IPv6. But because switching to IPv6 means that every router everywhere on the internet, every end system has to switch to IPv6 in order for all the traffic to be done, and everything has to be configured again with IPv6. All this time, they are still working on it. It's not yet implemented fully. So some networks can handle IPv6, but because of the legacy of IPv4 is so strong, we are still stuck with IPv4, and there are workarounds that are being implemented now to work with that. So, what does the IP address do? What does the IP address do? The IP address is gives you the end destination. So in the header, we saw that we have the IP address of the BRON, so the source, and the destination. So from the first end system to the other end system. Every address contains 32 bits, and we are going to go deeper into this 32 bits story. Basically, it has these four numbers with a dot between, and each one of these numbers uses 8 bits. And in total, we get 32 bits. There's a network part, and there is a host part. We're also going to talk about this now. The network part is always the left side, and the host part is always the right side. And focus a little bit on these things, because soon we're going to start solve some numbers, and you need to know this information. So pay some attention. The left part is always the network, the network tail, and the right part is the host tail, the host part. The amount, so the size of the network part and the size of the host part can differ. So only the first number can be the network part, or all three first number can be the network part. The size of the network part and the host part are decided by the subnet mask. So I think if we go to the, let's see. So, subnet masks, as you can see, they look something like this. You have already seen them, and today, finally, you will know what the mystery is of these 255s. Every 255 refers to 8 ones. And these ones, when you have ones in the network DAL, this means that in the IP address, then this means that it belongs to a network DAL. And if you have a 0, it means that it belongs to the host DAL. Now, how do we transfer these 255s to these ones? It's basic binary counting. So if I switch again to my other slide, let's see. You can see here that if I have only one bit, so if I have only one number that I can switch between 0 and 1, you can see that I have only two alternative states. It's either a 0 or a 1. So with only one bit in binary, and of course we know binary is easy because binary is either 0 or 1, so you can also transmit the electric signal. On is 1, off is 0. So computers like to talk with zeros and ones because it's easier than to communicate between the computers. Okay, so we have 0 or 1 with 1 bit, which means we have a total of 2 conditions. If we have 2 bits, then we have 2 combinations. Basically, it's the same as this one, but then we add 1 bit in before, and then here, so this is the same, 0 or 1. We add 1 bit before, either this bit is 0 or this bit is 1. So basically, we will multiply this number by 2 to get 4. And then the same thing is repeated here. If we have a third bit, then it's the 4 conditions, and then we add another 0 before them. Here, the first bit is always 0. In the second term, the first bit is always 1. And then we have 8 different conditions. So every time we add an extra bit, we multiply by 2. And if we go all the way to 8 bits, so 8 ones or 8 zeros, then you see that if we keep multiplying by 2, we go from 2 to 8 to 16, 32, blah, 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 all the way to 256. So with 8 bits, we have 256 different conditions. Now you will say, but Hani, the mask is always ends with 255. Why does it always end with 255? Because it starts with 0. Exactly. So from 0 to 256, sorry, from 0 to 255 is 256 different alternative states. Okay, this part clear? These things are also going to be directly related to the third assignment. So it's also important to pay attention here because it will also be applied directly to the third assignment. So when doing the assessment of the first 2 assignments, things were not too clear because they were not completely related to the lectures. So I was also kind of tolerating it a little bit. But for the third assignment is completely related to this lecture, so I will expect you guys to know this very well. Okay, so we have 8 bits, and then these 8 bits, either 8 ones or 8 zeros, they correspond to these 256 states from 0 to 255. And we will start calculating now these addresses together. You can see that, so if we have a mask of 255, 255, 255, 0, then the last part, so the last
8 bits, thank you, is are zeros. If we have 255, then all the bits are ones. All bits are ones, refer to 255, if you translate from binary to decimal. When we have 3 255s, they are transformed into 3 times 8 1 bits, and if you just count them, then they will add up to 24. So this is the shorthand. If you don't want to write 255 3 times and it's 0, and you want to make it write it in shorthand, one way to do that is /24. Okay. If we have if we have these also as zeros, and we have the rest as only the first 2 parts as 1, then it will be / what? Sorry? 16, exactly. And if only the first 8 ones are ones and the rest are zeros, then it will be /8. Okay? So it's not rocket science. It seems a little bit complicated, but actually you're just counting the ones in the subnet mask, and we know that each number of those represent 8 ones. So it's like 8, this is 8, this is 16, this is 24. So this subnet mask shows me that this subnet is a /24 subnet. If you understand it, then it's really easy. As always, it's always the case. Okay, examples. Let's see. So we have this network, and we have this subnet mask. Which part is the network part? Does anyone know? Yes? The first 3 bits, so it will be 145, 52, 123. And the second half, what do we call that? Okay, well, people are listening. Okay. So the network address is always the first, the network tail, so the network part, and the rest we put it as zeros. So we see that if we give this address, and then the last bit is 0, this is always reserved for the network. So if you assign an IP address to an end system and you make it a 0, this is not acceptable, because the 0 is always reserved for the network address. And when you see this address, you know that this is not an end system, this is a network. What does network address mean? So let's say that you have a small company, and the small company has about 254 computers. Then you will request a network, and you will be assigned this network. So it will be 145, 52, 1230, and then this is your network, and you will start from 1. Your first computer will be this network, and the last number will be 1 instead of 0. And then you will start counting up 2, 3, 4, 5 until 254. Can you use 255? No. Okay, why? Okay, cool. So people advanced here, they already did some network. 255 is also a reserved number. When you send any packet to this address, and in the end is a 255, then this will not be sent to a specific machine on this network, it will be sent to all the machines on this network. And sometimes this is useful if you are looking for a machine but you don't know. So you know that there is a printer on the network, but you don't know what is the IP address of the printer. You will send a request for a printer on 255, and then the printer will, every other machine will ignore that packet, the printer will see it, and it will reply like, okay, I'm the printer, this is my IP address, and then the communication can start. So .5 is the host deal from the IP address. And the alternative notation is /24, because we know that for each 255 we will add 8 to the IP address. Let's see. Shall we take a small break? Yes. So 10 minutes. We'll be back at 11:35. Thank you.
Je hebt het wel niet die klassisch waren of niet? Dat is perfect op ons. Oh, wauw, hij gaat 3-5 in.
Ik denk dat je niet doet in de nee, dit is zeker.
Maar hier is geen gate, dat moet je super zo'n man, zo'n woord lichten, dan moet
Maar ik vind het wel
Ja, maar als je het doet wel zoiets. Ik wil hier.
Ja, precies, maar dat is natuurlijk daar so disturbing.
De stream ook al is bijna al nu
Oh ja, ik kan al kiezen, ik heb het niet gedaan. Ik kan kiezen voor...
Wat we nu doen is zeg maar voor je punt voor de bestaande video op YouTube. En dan weer bij
Maar dus de definitie, Niels, ik ben erachter dat
Maar ook die dingen waar je aan het ja, dat is ook weer opzoeken. Dat is ook dan kom ik VR. Dat moet natuurlijk bij andere moet eigenlijk nog wat anders doen. Ja, doe het. Nee, ik moet niet met van zo'n video maken. Zeggen, vergeet niet te liken. Ik had vorige week, ik opende de NOS en er was een nieuwsartikel over YouTube. Kijk, het is zondag met Lucas en die gast had het stukje. Ik ging helemaal stuk. Ja, ik vond het geniaal. Ik ben zeer zwaar in het spel. Ik heb het bij dit boek holy shit, ik hoop dat ik niet een beetje bij je weet, als er dit gaat gebeuren, bijna 1000 mensen. Dat is in 1 jaar tijd het veranderen.
Nee, klopt. Ik denk eigenlijk de beste voor. Ja, volgens mij heel
kan nog steeds gewoon
I'm not even trying.
Ik ben het bal Ja, ik ben Paul. Paul heeft 18 vrienden. Ik dacht dat ik bij een vriend had. En nu ik ook.
What's up now?
You are now. Maar ik heb ook weer een zoek op levens. Ik wil dit ding uitzetten.
Nee, dat is mijn buis.
Het voordeel van de beta bestuurssysteem is dat je gewoon een beetje high five. Ik heb nu een Ubuntu 17.10, maar het is ook zwaar beta.
Okay, let's continue.
Zo zit het nou wel in.
So we saw that this is the IP address with this mask. It means that the first part is the network part. So wherever you have 255 is the network part, and whatever is 0 is the host part. And this notation, if we have this notation, is exactly the same as this notation. Okay, so this part of the IP address gives us the IP address of the end system, and then this part of the IP address of slash and 24 gives us the subnet mask of the IP address. No, the subnet mask of the network. What if instead of a slash, this was, so if this was the same number, but with a double point, so a semicolon, and 24, what will the 24 be? Okay, very good. So then it will be the port that you are trying to communicate with on this end machine. If it's a slash, then it will be the subnet mask. So another example, we have, you guys are experts by now. So we have this number, and we have this mask. So what is the network address? 16.0.0.0. So all these zeros are carried over here. And then what is the host address? Ja, dus punt 123, this, punt 123.12.17. Exactly. Okay. And, yeah, so after the slash, it will be 8. Third example, so when it's 16, how big is what's the subnet mask? Need the mask. So it's 25250 and then no, klopt. That is, okay, so this network address, so host, no, subnet mask. Never mind. And we skip like this. Okay. So okay, here's the exercise. Let's see. Oh, I guess you guys don't need it, but oh, you have a question? No? Okay. So since we already have the gear over here, let's try to use it. So we have but then the answer is 0. Okay,
So we have this address and then slash 16. So on slash 16, it's 2 times 255, so 255,255,00, because each one of those is an 8. So this will be another 8. Together they will be the 16. Okay, so this will be our mask. And the network address is whatever the mask keeps. So this part of the address will be the network address. And then these zeros will take over these numbers. So this will be our host address. So the host address will be 127.129. This will be our host address. Okay? And then this is the broadcast address. So the broadcast address, it will use the 255 wherever we have zeros on our subnet mask, so that you broadcast also for the computers that are on the second level. So whenever we have 00 in our in the address, then we are talking about the address for the whole network. Whenever we have 255, we are talking about the address for the whole, the broadcast address. Whenever you send a packet to this IP address, then you broadcast it to the whole network. Yeah?
Routing die wordt vaak als host nummer 1 gezet.
Yes.
En is dat standaard of kan je dat aanpassen?
So the router is a good question, something I didn't handle here. The router is usually the router that you have on your network that is connected to the internet. What did we call this router before? Do you remember? Sorry? The default gateway. Yes. So the router which is connected to the internet, the default gateway, is usually the one that starts that has the first IP address. But this is, even though this is a standard practice, it's not part of the standard. So you can actually have another number for your default gateway. But the network address having zeros, so the network address having these zeros and the broadcast address having 255, this is part of the protocol. So these have to be this way. The default gateway can be another IP address. That is still acceptable. Yeah, I did. Dus stel dat je een printer heeft, een netwerkprinter, en dat printer is verbonden op het netwerk, en iemand probeert om die printer te vinden, maar dat adres is niet bekend in je computer. Dus wat jouw computer kan doen, is een aanvraag sturen naar de broadcast IP-adres. Is er een netwerkprinter hier aangesloten in dit netwerk? En dan alle machines krijgen dan deze pakket met de aanvraag, met de vraag. En dan iedereen negeert deze pakket, behalve die printer. En de printer stuurt een antwoord naar die sender, dus naar je computer misschien. Hey, ik ben een netwerkprinter, ik zit op deze IP-adres. Daarna wordt de communicatie alleen maar tussen je computer en die netwerkprinter. En als je naar de Blackboard gaat, dan extra theorie, krijg je extra video's, geen tentoonstof, maar precies een voorbeeld over wat je moet vragen. Dus hoe kan je een broadcast sturen naar het hele netwerk met encapsulations en alles in envelopjes? Dat doet een andere docent van de Haag. Ja, dus dat was een voorbeeld van dit soort broadcast. Ja? Hoeveel hosts je hebt al? Hoeveel hosts passen in het netwerk?
Dus stel je jouw computer heeft nummer 4.
Ja. niet echt. Dus als jij dit IP-adres heeft, dus als je dit IP-adres heeft, dat betekent niet per se dat jij 129 computers hebt. Want misschien is dit nummer gewoon random gegeven aan het eindsysteem. Misschien waren er 128 machines en je bent 129, maar dan de andere 128 zijn naar huis gegaan en dan ben je de enige. Dus deze IP-adres betekent niet per se dat je de nummer 129ste machine op je netwerk bent. En er zijn ook geen standaarden of protocollen hierover. Dat kan gewoon ook een random getal zijn. Maar wat je wel weet, met behulp van de masker, is hoeveel machines passen op deze hostdeel van die IP-adres. Dus we weten, so we know that if we have here, so let's keep it easy. If we, let's say that, can I erase all this stuff? So, let's say that I have here, instead of this mask, that I have here a mask that is, let's see, 255, 255, and 255, and 0. Okay? So this is an example of what an exam question can look like. So maybe you guys want to pay a little bit attention. So let's say that this is the mask. So forget about this mask. Let's say that this is the mask that we have. And then the question says, how many hosts, no, not hosts, how many end systems, how many end systems, how many end systems can you have on a network with this subnet mask? So what will be the answer? Yes. Yes. It's 254. Why?
Because you do 2 to the power of 8 minus 2. So 6 minus 2.
Yes. And 1 minus 2?
Because it's network address.
Because the number 0 falls out because this is the network address, and number 255 falls out because it's the broadcast address. So it's 255. No, 254. Maximum number is 256, and then you take 2 out of it because, as we know, it would be so it would be this would be 127. This will be the network address, and then the broadcast address will be 127. So this will be, this is taken, this is minus 1, this also minus 1, so 256, minus 1, and then the result will be 254. Okay? Is this clear for everyone? If you don't understand this, then you'll have trouble with the exam. Does this calculation make sense to you? Yes? Good. Now the question is, how many end systems will you have? Now this is a little bit more complicated. Let's see if you guys will fall in the trap. If you have this subnet mask, okay, so /16, 2 times 255 and 00, then the same question is the number of potential end systems. How many end systems can you have here? You already answered, you moved on. Does anyone know the answer to this question?
Zeg maar,
So, hoeveel endsystemen passen op deze host there. Yes? Dus 254 keer 254. Dat is niet correct. Dus jullie collega zei 254 keer 254. Maar dat is niet het correcte antwoord. Omdat. Ja?
256 keer 256 en dan min 2. Want dan heb je de broadcast en het netwerk.
Ja, maar één.
Nee, maar je hebt nu per...
Stel
Stel het eerste getal is bijvoorbeeld, dan heb je 1, 2, 3, 4, maar per subnet daarin heb je ook broadcast, et cetera.
Dit is echt verwarrend.
Dat is de broadcast. Bij netwerkadres heb je al die 0 plus 0. Dus je moet ze nog steeds afhalen.
Ja, daarna is eerst 256 en 256. En dan min 2 voor de broadcast en voor het netwerk.
Zo is het ook wel 0.
That's actually a good point. If it's 1, then 0. Is that a broadcast address or is that
Ja, maar kijk, punt 1, punt 0. Dat is gereserveerd. Punt 2.0 is ook gereserveerd. En punt 3.0 is gereserveerd. En punt 3.2 moet gereserveerd zijn. En punt 4.
No, I think it's only 0, 0 is reserved. If it's
Ja, maar heb je niet een punt 0 en een punt 2.5 nodig?
Jawel?
Ja. Dus daarom is het denk ik 2.5.
Ja. In ieder geval, ik kan er helemaal 64.216.
yeah.
Dat goed denk ik wel.
So actually, I will check the answer for this. I don't know it. I'll check the answer. Okay.
Maar als je dus 2.5.
Dus de antwoord op dit komt volgende week. Ik weet het ook niet zeker of het zoals Luke zegt, dus 256 keer 256 min 2 of 256 min 2 keer 256. Ik weet niet zeker welke is het correcte antwoord. Maar goed. So let's, I'll answer this next week. So you guys have to come next week to see the answer for this one. Let's continue with the presentation. So let's okay. So subnetting. What is the point of having a subnet? Oh damn. How much battery do we have? Okay, let's load the screen. We'll keep working until the battery runs out. What is the point of having subnets? The point is that you have one network for the whole school, for example. So here the example of the Hasselhoff school is given. And then depending on the size of your organization, you will be assigned a specific number of IP addresses. So here for the school, we see that the school here has more than 254 devices. So the school requests to have a subnet that is bigger than 255. And that's why you see that here the school has this IP address that is 245.52. And this is the network that's available, and then it has around 50,000 computers that can be connected with unique IP addresses within the network. And then you see that if I look at the settings of my computer, so if I go to system preferences, I will jump into the if I go to my network settings, and I see my, let's see, yeah. So I see that you see that I am indeed within this network.
So within the 145.52 network, my IP address is this IP address, and then you see that I have another subnet mask. So I don't have the subnet mask of the whole network, which is 255, which is /16, which is 2 times 255.00. And why is that? That is because we are in a subnet. So the subnet that is given to the host of the whole has a /16, so it has it can assign all these IP addresses, and then the host of the whole will continue to divide this subnet into smaller networks, and then these smaller networks can be assigned as they wish. They can assign part of the IP addresses to the students, part of the IP addresses to the teachers. They can assign part of the IP addresses to different locations, in Zoetermeer, in Delft, in The Hague. And they can also assign some part of the network to like the grade systems, so that they are more secure than other IP addresses. So things of that nature can be used within the network. So how many hosts and how many subnets? This is a question. If you have a /24, so how many /24 subnets fit in a /16 subnet? Oh, the answer is already given. Oh, well, okay. So, how many subnets fit inside the /16 subnet? That will be 256 subnets. Why is that? Yes?
The first two are the network part, and then the first three, and then you can change it to 256. /24 is 4 hosts. I can't really explain it well.
Yeah, okay, it's hard to explain without writing down answer. Okay, so it's so let's try to write it down. So let's see, we have go to this thing again, and we come here. So we have a /24. So let's say 145.1. Whatever, so let's say .10.00. This will be the .0.0. This will be your /24 subnet. So this will be your network. And then how many /16 subnets? So /16, if you remember, is sorry, I have to all the way up. This is /16. It gives you this subnet, right? Yeah? Okay. And then how many /24 subnets can you fit inside here? So this will be /24 will be something like 255.255.255.0. Then how many of these can you fit inside here? And then the answer is 265. Why? Because here we don't have the .0 and .255 reserved. So we can use the whole range of this second address. So the first subnet will be 145.10.0. Let's see. Yeah. 0.0, this will be the address for the first subnet, and then the 145.10.1.0, and then etc. until 255.0. 10.145. And then, so from 0 to 255, you will have 256 subnets.
And for subnets, we don't reserve the 0 and the 255. They can also be used. But when you specify the last bit for the IP addresses, then indeed you have the .0, this will be the network address, and then the 255, this will be reserved for your the broadcast address. Is this part clear? I think there's a little bit of confusion. Also not 100% on it, but we will go over it again next week. So here's the question. In practice, you will also lose one other address. And why is that? It was already mentioned. The gateway. So another IP address that you will lose for your from your network addresses, and that is always given to the default gateway. Usually it is the first address, so it will have the number 1. So the last bit here will be 1. Which this one, then it's usually assigned to the default gateway of your system. Let's see what the next slide is. Yeah, it's another example. We have 5 minutes, so let's see if we can look into that. So provider use a network like this. So this network has a subnet mask of 8, so this will be 255.0.0.0. How many users? Default gateway. So including the default gateway, how many users? How many usable IP addresses do we have on this subnet? So each subnet, so this network will be divided into other subnets, and then these subnets will start from this one, then 255.0.1.0, and then etc. until 255.0.255.0. And the next, when you go further, you can then start with this at 1, so 255.1.0.0, and then continue on and on and on until you keep going until this one 255 again, then this goes into 2, etc., until you end up with 255.0. So it's 255, and then when you reach this limit, you increase this by 1, then you go up to 255 again, then you increase this by 1 again. So the total number is 255 times 255. So this is the total number of subnets that you can have on your network. And for each of these subnets, you can have 254 addresses. So for each one of these subnets, number 0 is reserved, and number 255 is reserved. Only the numbers that are in between are available. These are, if you add them up, there are only 254 addresses. So inside each one, in één subnet zitten er 254 bruikbare IP-adressen. The lowest subnet is this one, so 00. You start from this address, and then the highest subnet is 11.255.255.0. And then when you give the address, you also have to specify the subnet mask size. So the subnet mask is 24, because you see, we are using all this as our subnet mask. So for all these networks, the subnet mask size is 24 bits. And then you start again from 00, 01, 02, 0, until 255, 255. Yeah, is that example clear? Are there questions about this example? Yes? Ja, dus het is van 0 tot 255, dat is 256 verschillende IP-adressen. Oké, maar 2 zijn gereserveerd. Dus per subnet, er zijn 256 min 2, min de gereserveerde 2. Dus in totaal zijn er 254 beschikbare instanties. Ja? Als je... Ja, precies. So this subnet on the bottom is a subnet. So it's a division of the subnet that you have already taken. The first subnet is 11.000/8, and then you divide it into additional subnets with the /24. Yeah, it's a subnet and a subnet. Yes, other questions? It's a little bit complicated, a little bit confusing, yes?
Met die onderzoek, er staat netwerkadres. En dan 11.0.0/24. Hoe dat geen 8 zijn? Want die slaat niet op het netwerk, die is de host. Dus de eerste 4 is voor het netwerk, en dan de laatste voor de gezelligheid. Die zouden ook anders zijn. Dat is wel een host.
So
Ja.